The question I have for you is, what do you think I have in this bottle here? I'm sure that without any shadow of doubt, you can guess it's something very heavy, obviously, because it's being balanced up against a bag of oranges and 2 cooking apples. But furthermore, I'm sure that you'll know it's mercury, one of the densest liquids, certainly the densest liquid at room temperature and pressure. So what on earth has mercury got to do with a meeting of the Meteorological Society? Well, let me tell you the story. It was in the beginning of the Michaelmas term in 2018, when we started having our Friday afternoon meteorological meetings, that a certain young lad from year 7 called Alex started coming to the meetings. And I was immediately, in fact, we were all immediately absolutely amazed by his stunning knowledge of weather patterns, the atmosphere, the physics of the atmosphere, how weather changes and all that. And so Alex knew so much, and I've never claimed to be a great meteorologist. In fact, I've never claimed to be at all. I'm an interested enthusiast of meteorology. And I've been taking readings, simple readings for many dozens of years, I suppose. And I'm very keen on weather forecasts. I just love following the weather. I just find this interesting. So Alex was here, was someone who clearly knew a huge amount, far more informed. So I started getting Alex more and more to participate in the meetings actively, and indeed to explain things to us, all of us, which we were all very impressed with. However, it was some stage in November 2018 that I just dropped a casual comment to everyone. I said, oh, by the way, does anyone have their own meteorological station at home? Do any of you take readings? Of course, Alex immediately said, sir, of course I have everything. So I said, amazing, Alex. So I presume you have a maximum minimum thermometer? Of course. Do you have a hydrometer? Of course I have a hydrometer. Do you have a sun gauge? Of course, etc. So the things he had were continued to be very impressive. And then I said, but do you have a barometer? Of course I have a barometer, sir. And I said, well, what sort of barometer is it? Now, for the first time, Alex stopped in his stride. He said, what type? What do you mean, sir? I said, well, I mean, do you have an aneroid barometer or do you have a Fortin barometer? And he said, well, sir, quite honestly, I'm not sure that I've ever heard of a Fortin barometer. I suspect my one is an aneroid because I've heard of that. And I said, what? You've never heard of a Fortin barometer? Then I said to everyone else, has anyone else heard of a Fortin barometer? Blank expressions. So at that stage I thought, brilliant, I've won up. I know more than Alex on at least one aspect of meteorology. I knew what a Fortin barometer was. So I didn't talk too much about this barometer business any further. I just simply we briefly discussed how an aneroid barometer works. And in fact, we have one in room C1 because on the front bench at room C1, there is in fact a barograph, which sometimes people think is a seismometer. That's not a very bright comment to make, by the way, but never mind. It is a barograph. It measures the pressure, and the pressure is measured as a function of time. And the type of barometer in there is also an aneroid barometer. So I've got one here, which I bought this, by the way, at Hornsey Auctions about 20 years ago for a tenner. Unbelievably good value. Not only that, it came with a makeup mirror as well. So not only can I tell the pressure, I can also look at myself to see whether everything is in order. Now, I just wanted to show you very basically, an aneroid barometer works on the principle that there is a partially evacuated tin in there. As the air pressure changes very slightly, so obviously the tin expands and collapses, and it is linked up to mechanisms which enable a dial to change, and I can just rotate. You see, this is where we set it with. The black one tells you our reading at the moment, and it tells you something about the weather. So you've got stormy, rain, change, fair, very dry, and all the rest of it. Now that, of course, is partly related. It can't exactly tell you that, because otherwise there'd be no point in making weather forecasts. But the point is that the pressure does tell us quite a lot about how the weather is going on. And the point of this line is you reset it so you can tell from one visit to the barometer to the next visit whether pressure is going up or down, and therefore you can make some sort of a deduction for your own interest as to how the weather might be changing. Now that, of course, is the aneroid barometer. And then I thought to myself, well, I'm not going to talk too much about the Fortin barometer, except for I did say to the pupils that this is a most important type of barometer. Not only is it supremely accurate, but also the principle upon which it works is one of the most important principles of the whole science, of the world of science that we live in today. And I decided, I just left it at that, I didn't tell them much more about that, but I decided I was going to surprise everyone. And surprise I did, you see, because what I did, I then thought to myself, I must buy myself a Fortin barometer and bring it to school and show it to everyone. And that's exactly what I did. I went on eBay, of course, and then I started looking to see what sort of barometers were available. And you know what, I have to tell you the truth, there wasn't a great choice. Most of the Fortin barometers were old school models, or models that had been used in the 50s and 60s. They were not at all in good condition, and they were selling for about 200 to 300, or attempting to sell them for £200 or £300. So I then went on to the antique barometers, and among the antique barometers there was a section called stick barometers, and it was in the section called stick barometers. Incidentally, I had no idea what a stick barometer was, but I started poking around, that I came across a beautiful example in a mahogany case of a Fortin barometer made by, I think it was Baird and Tatlop, top manufacturer, early 20th century, and it was going for a ridiculous price of £199. I thought to myself, this is unbelievable. So I immediately copied in the photos to one of my best friends, Jonathan Ryder, who's an expert on these instruments. And Jonathan looked at the photo, he said, Szydlo, don't waste a moment. This is the bargain of the century. Go for it. I followed his advice, and you know what? I bought it. And the great day arrived on the 26th of February last year, when I drove down to South Wales, 250 miles, return trip in my Triumph Herald. And of course, you'll not be surprised to know that the man selling the barometer was an unbelievable character, but that will take up a whole separate meeting of Metsom just to tell you about him. But that doesn't matter. The fact is, I brought back the barometer in a great, for me, which was a great success. And then, of course, I presented it, I brought it to the school, and sometime in I think it was in March last year, I gave a special Meteorological Society meeting about it. So today I wanted to show you this barometer. I've got it here hanging behind me. It is one of probably the most beautiful things in our house. And before I show it to you, I'm going to explain to you the principle upon which it works, and why the principle upon which it works is such a vital principle in our understanding of matter. And in order to explain that, I have to go back over 2,000 years in history. Man has always been interested in ultimately what are we made of. And about 2,300 years ago, during the times when Greek philosophy was very prominent, and there were some brilliant natural thinkers around, natural philosophers, one of whom was called Aristotle and another was called Democritus. There were many others, of course, but I've just mentioned two, because these two philosophers had completely contrasting opinions as to about ultimately what matter is made of. Now, according to Aristotle, there were four elements: earth, fire, air and water, and everything grew out of those four elements, which were combined in various proportions, and the word transmutation explained how eggs changed into chickens, how seeds changed into grass, how iron went rusty. It was the same word, it was a complex system. And one of the most important ideas in Aristotle's philosophy was the idea that the whole of the universe is full of matter. Matter occupies everywhere. There is matter. There is no such thing as an empty space or a vacuum. Nature abhors a vacuum. That was a very, very, very important idea in the Aristotelian philosophy. Now, Democritus, by contrast, had proposed that actually all matter is made of tiny particles. He called these particles atoms. Atomos is, of course, the Greek for very, very small. And Democritus suggested that everything was made ultimately of these small, tiny particles. He didn't have any ideas. This was just a philosophy. He couldn't prove it. He had the ideas, but he couldn't prove them experimentally. So he presumed that wood was made out of tiny atoms of wood, metals were made out of tiny atoms of metals, and so forth. And the question then arose, well, Mr. Democritus, what is there in between the atoms of wood or the atoms of a metal? And the answer was, well, there must be nothing between these atoms, because the atoms were supposed to have perfect geometric shapes. They were supposed to be octahedrons, spheres, cubes, all sorts of pyramids. They had a whole variety of shapes. And there's no way that you could pack them in such a way as to fill space entirely. And so Democritus had this idea, and that was his idea. And then there was sort of a debate which lasted several dozens of years, I think. But the fact is that Aristotle's ideas became very, very widely accepted. And Aristotle's ideas of the four elements and the way that they interacted and transmuted to give rise to all the changes in the universe became accepted as the fundamental tenets of natural philosophy. From this philosophy stemmed the proto-science of alchemy, where scientists, where alchemists for hundreds of years, almost 2,000 years, tried all sorts of experiments, developed extraordinary apparatus, experimental procedures with the aim of either making an elixir of life or a universal solvent or prolonging life, all sorts of remarkable aims they had, these alchemists. Now, we know today that, of course, this idea of four elements and the idea of transmutation, you can't actually construct experiments and make progress on that. But at the same time, the arguments were so strong from these philosophers that they continued to dominate natural philosophy. Now, this is where the big change came. It came in the middle of the 17th century, and it arose from purely practical considerations. And let me tell you what the practical considerations were. They were concerned with mining. Now, mining is something which has been practiced by the human race ever since the dawn of humanity, 1 million years ago, 500,000. We have always dug things out of the ground. And as the 16th, 15th, 16th, 17th century developed, so we were digging deeper and deeper for getting more minerals, for making better metals, ceramics, glasses, and so forth. And as we started digging deeper and deeper, so the technology and the problems which we came across became greater and greater. And one of the great problems confronting the miners of the 13th, 14th, 15th, 16th centuries was the problem of flooding. Because the deeper you go, the more likely water will always fall somewhere lower. And so mines became flooded. And mines were flooded, or depends where, not all, but flooding was a big issue. And so people derived various ways, designed various means of extracting the water from the mine. Now that itself is a huge history, and I could just mention the Greek engineer Archimedes was a person who developed an early type of a pump. But during the 17th century, 16th century, the technology moved forward. And as a result of that, people wrote books. Now, one of the most famous books on mining technology was written by the German Georg Bauer. Now, Georg Bauer literally means George Farmer. However, because people used to Latinize their names in those days, he was actually called Georg, he was called Agricola. Agricola, which of course means farmer in Latin. So Agricola published a work, which I've got a copy of here. The work was called De Re Metallica, which is on metallic things. And it was huge, 1556. It is a classic of a world scale. Now, I have a modern reproduction of this. By the way, it's very, very cheaply available, 15, 20 pounds or something like that. It goes up to, I don't know, 600 pages and phenomenally beautifully illustrated. And I have actually taken one of these illustrations and I've coloured them in for you. Now, the reason why I've coloured them in is not because I'm being silly or because I like colouring things, because I do, by the way, but this is to illustrate what I'm on about. And you see, what we've got demonstrated here is a water wheel which is turning. It's driven by the stream which is flowing, and it's got, in black, I've drawn the mechanism for operating a series of pumps. And these pumps, 1, 2, and 3 down there. This is, of course, not drawn to scale. I've shaded them in brown. And the problem is that they were getting water out of the bottom of this mine. Now, the big problem is with these pumps that they could only draw water up a certain height. And that height was 34 feet, approximately 10 meters. And no one could understand why it was that you couldn't draw the water any higher. Now, that was what instigated a whole load of research into the phenomenon of pressure. In fact, how is it, and the pressure, but related specifically to air, because air was a big topic in the 17th century as well, and people were asking themselves the question. Air, of course, was one of the 4 Aristotelian elements, but people were beginning to study the chemical and the physical properties of air. One of the greatest scientists in this field, natural philosophers, was the Irish natural philosopher Robert Boyle, famous for his Boyle's law, of course. And the fact is, though, that air became a big topic, and the sort of questions were people were asking: is air a substance? Is it a spirit? Does it have any weight? Does it not have weight? How does it flow, etc.? There are a whole large number of questions which were being answered. And among those was the concept that air has weight. It can weigh something. And therefore, people reason that if air weighs something, then the air around us must be very heavy. And if it is heavy, it can exert a pressure. Now, it was at this stage that people started trying to understand how these pumps worked in terms of air, the weight of the air balanced against the weight of the water that was being lifted. That was, in a nutshell, what they were trying to do. Now, because these pumps were so huge and because they were 10 meters high, it was difficult to carry out investigations with water to find out how pressure works. So scientists started experimenting with mercury, which I've got here. And the reason why they experimented with mercury is because it has a much higher density than water, and therefore a column of mercury which would be supported by the atmosphere would be much shorter. Now, the great breakthrough came in the year 1643. In 1643, the Italian physicist, natural scientist, Evangelista Torricelli, constructed for the first time what we know, the barometer, as I'm going to explain to you in a minute, but the principle upon which the barometer functions, that was the great breakthrough in science. For Torricelli filled glass tubes of various lengths. Now, the Italians, by the way, had developed brilliant skills in glass blowing and glass manufacture, especially Venice was the great center for this, and we're looking at the 15th, 16th centuries, and therefore they were able to make beautiful long tubes which serve, by the way, for thermometers, for chemical experiments as well. There were a whole range of things. And among them, of course, for physics experiments. The science of physics was evolving as an independent branch of natural philosophy. And these tubes, which were constructed like approximately this length. Now, what Torricelli did, he filled these tubes of various lengths with mercury. And then he turned them upside down inside a bowl of mercury. Now, the results which he obtained, I have got for you going to show you in this book which I've got here, which is called Ordinary Level Physics. Now, interestingly, the reason why I'm showing you this book, I'm particularly proud, because when I was at Latimer Upper School in the 1960s, my physics teacher was the author of this book, A.F. Abbott. He taught me physics. He was an amazingly humble man. You would just never think that this man had written a book which sold 7 million copies worldwide. This is the most widely read physics book of all time for school children. And I wanted to show you, because in this book we learned about the Torricellian vacuum and about the Fortin barometer. And the principle is illustrated here very straightforwardly. We have, this is the long tube here, and atmospheric pressure acts on it down here like that, you see, and the column of mercury is supported up to 76 centimeters there. Now the tube is longer, so the question became, what's inside there? And there you see, if you then tilt the tube, then it gradually fills with mercury. And you see, the answer to this question is, what is there? If it was full of mercury before, what is there there? Now, the answer is nothing, a vacuum. Evangelista Torricelli had demonstrated for the first time something which people just could not believe or understand. But the fact is, he had shown it by experiment, and it was experiments that form the basis of modern science. Now here you see is the barometer, the Fortin barometer. We used to have to learn how to draw this and how it works, but I'm not going to focus on this at the moment. I'm going to just put this book down here and say that the Fortin barometer exploits this property of the atmosphere changing its pressure due to the different amount of columns of air, and which move around as the weather changes. And using this Fortin barometer, it was invented, but the man was Jean Fortin, he was a Frenchman, and it was through him, you see, that we then developed accurate ways of measuring atmospheric pressure. And I wanted now to show you this barometer, which I've got here, in just a little more detail. So Oscar, if you could kindly come up, I just wanted to show you, because it's one of the most beautiful instruments. If anyone ever wants to come to see it, by the way, you'll be more than welcome, and I've got lots of things to tell you about it. I'm just going to very, very briefly outline the principle. So we have here a long column. This is a long tube which is filled with mercury, and the end of the tube is immersed in a leather pouch full of mercury. Now that leather pouch is full of mercury, and I hope you could see there is an ivory pointer there. Now that ivory pointer can be adjusted up or down by, there's a screw which you turn at the bottom, and you can raise the level of the mercury up or down. Now that's what we call a zero adjustment. And then you see, so you adjust the zero, the ivory pointer, and then as we move up, we see that there is another device which has mercury in it. And this is a mercury-filled thermometer. And if you look carefully, you could probably see that the temperature, I think, is about 20.5 degrees centigrade. That's what it was when I looked at it half an hour ago. And there's a very good reason for having an accurate thermometer. And then as we go up, then we see the make here, which is a Baird and Chatlock. This is a this is a top quality make indeed, you see. And then we have the scale. Now there are two scales. The right-hand side one is calibrated in inches, and the left-hand scale is calibrated in millimeters. Now 1 atmosphere pressure under standard conditions is about 29.92 inches, and 1 atmosphere in terms of millimeters of mercury is about 760 millimeters of mercury. Regrettably, this barometer is not reading accurately due to a small air bubble that's inside there. And I have not got the time, thank you very much, Oscar, and I have not got the time to actually, it's quite a significant undertaking. I've done a lot of research. Filling these with mercury is a very, very complicated process. So I'm simply delighted to have this, and as I said, to show it to anyone who would like to see it. So the barometer, now where would you find the barometers? Well, the answer can be certainly inferred from this beautiful painting which I have here. And that I'm sure you recognize as a sailor with a lighthouse. And it is, of course, the main reason why barometers, one of the most important reasons why barometers were used was for sailing. So if you went far in a ship, you needed to know what the air pressure was. You could use predictions of how the pressure was rising or falling, and you could then set sail and know roughly what to expect. By the way, the reason why there's a thermometer here is reading the vernier gauge here, that gave you a reading to within 0.1 of a millimeter of mercury. It was also very, very important for a temperature correction. Mercury expands and contracts, and so does the glass which it is housed in. And it's a remarkable. There is a formula, a fairly complex formula which you use to convert your reading into a spot-on, super exact reading of the pressure at any given time, taking into account the temperature. So then there is the Fortin barometer. By the way, you know, people used to carry these up mountains. Could you imagine hoisting one of these on your back in a rucksack up a mountain? And they did. The reason why, they used the barometer to prove to themselves that the pressure gets less the higher up you go the mountain. And of course, in the age of balloon flying, which the 19th century was, phenomenal amounts of flying was done. Hot air balloons, hydro, people used to take barometers to take scientific measurements. And you could use a barometer to estimate how high you were. All sorts of remarkable possibilities. Thanks to this, the Fortin barometer. Now, having explained to you a little bit about the physics of the mercury, the fact that it's got a very high density, and the fact that it was instrumental in the development of the modern atomic theory, because once the vacuum had been demonstrated, so people started saying, well, in that case, can we go back to the Democritian theory of matter being made of particles with nothing in between them? And so they did, of course. The theory became published. A more significant way of expressing it was John Dalton's atomic theory, published in 1807, and that had a profound effect on the development of the natural sciences, chemistry and physics. Incidentally, John Dalton was a fanatical meteorologist. He was colorblind, but he kept records for years of all the most extraordinary set of results for weather patterns at the beginning of the 19th century. But let us now start bridging the gap between physics and chemistry and mercury. And I wanted just to show you here a very brief introduction to a man who perhaps is known as the father of modern chemistry. And this is the man, Antoine Laurent Lavoisier, the great French chemist who formulated today's theory of combustion. Now, the reason why I wanted just to introduce you to this, because actually he made use of both the chemistry and the physics of mercury in making his greatest experiment, which was the thermal decomposition of the calx of mercury to produce both mercury and the gas which we today call oxygen. And I just wanted to quote for you this this short paragraph from his Elements of Chemistry, Traité élémentaire de chimie, published in 1789, translated into English and published in 1794. And I just wanted to read for you very briefly, because I'm now going to go gently onto the chemistry of mercury. I introduced 4 ounces of mercury into the mattress, and by means of a siphon exhausted the air in the receiver so as to raise the quicksilver, and carefully marked the height at which it stood by pasting on a slip of paper, having accurately noted the height of the thermometer and barometer, I lighted a furnace. Now, this is the amazing thing. He had already, this was 1780s, he had already recognized the vital importance of measuring air pressure and temperature. He used a mercury-filled thermometer, mercury-filled barometer, but that's a coincidence, should I say? But he had recognized the importance. And why was it so important? Because you see, when you are experimenting with gases, in order to calculate quantities of gases, we use volumes, but because gases are known as elastic fluids, we have to make adjustments in terms of pressure and temperature as to how much of the gas that we actually have. And already Lavoisier was a brilliant experimenter. He made his own apparatus. He understood. He was a supremely accurate quantitative measurer. Now, quantitative chemist, and I just wanted to say, he took 4 ounces of mercury. Now, that's what I'm going to do in just a second. Now, I am now going to make space here for some chemical demonstrations with mercury, and we will be finishing on those. So I am now going to ask Oscar, could you take away the scale with the apples and the oranges, and I will now make space for a short demonstration on the chemistry of mercury. Now, I'm going to show you first of all here, I'm going to start off the experiment, and then I will show you what I'm going to be doing. Now, of course, for Lavoisier, the important thing that he did, he investigated the oxide of mercury. Now, the particularly interesting thing about that is that if you heat mercury at its boiling point for a long period of time, it gradually oxidizes and it makes red mercuric oxide, which he found. But if you then scrape off the oxide and heat it to a higher temperature, it decomposes to release the oxygen and give mercury back. Now, Lavoisier described this absolutely brilliantly, and in fact today he described it quantitatively, and today I actually did the calculations. He took 4 ounces of mercury and he heated them strongly, and he made some, as I said, at its boiling point for 12 days, and he measured the volume of air that was absorbed, and he then found that by heating the orange product, he was able to achieve the same volume of air, which made splints grow very brightly and flames glow brightly. Now, by the way, this is my weighing boat. I don't have any plastic weighing boats at home. I've got a box of matches. So here, I hope you could see this beautiful, this is, by the way, roughly 20 grams of mercury. Thank you, Oscar. And what's going to happen now is I am now going to react this mercury. I'm going to chemically react this mercury with some concentrated nitric acid. Now, I'm going to do this experiment, by the way, lasts approximately 2 minutes, but I'm going to bring it up closely to show you. Now, at this stage, I'm just going to put on my goggles here, and I have in my flask here, I have 10 centimeters cubed of concentrated nitric acid. You can in fact slightly see the brown fumes above there. Those are fumes of nitrogen dioxide. It's fuming just a tiny little bit. So I'm going to now from my matchbox, I'm now going to pour this mercury in here. Can you now please watch? Oscar, could you go and turn on the fume cupboard now, please, as well? I'm going to be producing a little bit of NO2, a little bit of smoke, etc. So please watch carefully. I'm now pouring the mercury in there, and I'm going to bring this close up. The flask, by the way, is slightly wet. I hope you can all see that. This is most important that you can see this. And I'm now going to pour on top 10 centimeters cubed of nitric acid. Now, I have calculated, by the way, that I have an excess of mercury. Now, the amazing thing is that as mercury, which is, by the way, a relatively unreactive metal, As the mercury starts to react with the nitric acid, it reacts so pretty quickly. And I very much hope you can see this. And also, the first thing I think I would like you to be able to see is that it's bubbling. If you can see close up where the bubbles are being produced from the bottom maybe of the mercury, but you can also see a brown gas being produced. Now I'm going to swirl it around. I'm swirling it around now in order to increase the surface of the mercury, thereby increasing the rate of the reaction. And I have to tell you that the reaction is now proceeding. The gas which is coming off is dark brown nitrogen dioxide. Now that's a very toxic gas, but the honest truth is it's not that poisonous, and it's not something that I will be troubled with at all. We've got the fume cupboard on, and I will very shortly extinguish this reaction by pouring in some distilled water. So please, now I hope you all notice that green color, by the way. If it's gone a dark green, and maybe some of you are wondering, is it a mercury? Now can you see the gas coming out of the top? I am now going to neutralize the fumes, and I'm going to take, I have here, by the way, let's just put it down here, and I'm just going to, here I have some strong ammonia solution. This is, by the way, ammonia which I purchased from, it's used as a cleaner, and I'm going to just blow the ammonia over and make some white smoke. It neutralizes the nitrogen dioxide. There we are, and you see gradually, and that beautiful green color, that's the color that I'm particularly interested in. It's going slightly towards Oscar, but you see there's no problem at all. These fumes are slightly irritating, but the honest truth is the concentration is so low, even though it looks pretty fearful, I can assure you there's no great danger. Now, what I'm saying, what I can see now, and I hope you can see, is that the reaction has more or less finished. By the way, just in case there are any of you here who enjoy chemical equations, I'll give you the equation for this reaction. It's it's Hg plus 4HNO3 gives HgNO3 twice plus 2NO2 plus H2O. And that, of course, HgNO3 twice is, of course, the formula for mercury 2 nitrate. Now, at this stage, what I'm going to do, I'm going to extinguish the reaction by pouring cold water. By pouring in distilled water, please watch carefully and notice the interesting color change that results. Notice it's green at the moment. So as I pour water in, please watch carefully. And there you see, lo and behold, the green color has completely disappeared. It's been discharged. Now you see, why is that? What was causing the green color? Can you guess what was causing the green color? Was it anything to do with the mercury? No, it wasn't. It was the nitrogen dioxide dissolved in the nitric acid and in the mercury nitrate solution. Nitrogen dioxide, when it's dissolved in aqueous solutions of a high concentration, has a pale green, a green appearance. So what I've now got here, you can see some unreacted mercury at the bottom, and mercury nitrate. I'm now going to pour the mercury nitrate solution into 4 beakers, which I have here, approximately in equal amounts. Now, it doesn't really matter whether mercury goes in as well, because the honest truth is there is I'm going to be washing it all out in any case, so the mercury won't affect the reactions which I wanted to show you. So I'm just pouring. There you see the mercury just went into that last one there. And I hope, Oscar, you're focusing on these, excuse me for please asking you, and what I'm now going to show you is what I hope are some most interesting reactions. So what I've got here is mercury nitrate solution, to which has got some excess acid. But as I pour, and I'm going to add sodium hydroxide. Now, these are displacement reactions. Mercury nitrate plus sodium hydroxide makes sodium nitrate plus mercury hydroxide. Please watch carefully as I do this. I'll bring it closer up actually. Is it okay? It's okay. It's okay. So you could see it perfectly well. Okay, so here we go. And you notice initially, you notice the color is discharged because the sodium hydroxide is being neutralized by the excess acid. But as I carry on adding, you can see a light brown. Now it's gone yellow. And you see this dark brown, these remarkable color changes. You know, I really don't know what's going on, but the point is you can't deny that this is interesting. And so we have a yellow color, and as I continue to add more sodium hydroxide, we're getting more, the color will go, hopefully will go darker and end up with a chocolate brown. And that, you see, that is probably mercury hydroxide, HgOH twice. But the honest truth is I'm not that sure because there's quite a bit of unusual chemistry with mercury compounds. Now the next one I'm going to do, I'm going to add some sodium sulfide. Now this will make a precipitate of mercury sulfide. And we add this in here, you see, and you notice the color goes black straight away, and there is the black mercury sulfide which is present there, and we'll leave this standing for just a while there. And something very peculiar may happen there. Now, here we have potassium iodide solution. So this is going to make mercury iodide. Please watch carefully as I add a small quare. And there you see a beautiful yellow color. Beautiful yellow color. Add a little bit more, and there you see. Now that's a yellow precipitate, obviously of mercury iodide. But now I'm going to add some more to another sample. Please watch carefully what happens here. You see there's our yellow, just as we've got there. But as we carry adding on more, watch what starts to happen. The color starts to go darker and darker. And eventually we end up with this beautiful, intense orange color. Now this, of course, is mercury iodide, HgI2. Now the honest truth is, I don't really know what the exact formulae or the substance is here. And can you see, this was black a minute ago. Can you see the blackness has now been precipitated, and we have a murky white color there. And here this is now gone chocolate brown. And just to finish off here, we'll just now pour some water into here. This is, by the way, tap water. It's not distilled water, it's tap water, just to wash out our flask. And if you see now, as I pour it in, you'll see the most remarkable thing. Can you see yet another color? Now this pale yellow is due to mercury carbonate. You see, tap water contains impurities. It's hard water, and these tiny amounts of impurities are precipitated down. That's why solutions, mercury compounds, are always dissolved in water. In fact, any heavy metal compounds, lead, mercury, if you want to make a solution, you must use distilled water.